So thanks, Demetrius, for the introduction. And welcome to the most exciting session of SOSP. So I'm going to kick the session off by telling you about Concord, which is the system we've built that enables data center applications to sustain microsecond tail latencies and high throughput without requiring access to specialized hardware or application level assumptions. So this is joint work with my colleagues Musa and Marios and my advisor, George Candea. So data center applications are expected to meet stringent microsecond scale tail latency service level objectives or SLOs at individual servers. And this is because these applications typically fan out each user request across hundreds or thousands of individual servers, with the end-to-end response time being determined by the slowest individual response. And these tail latency SLOs are only expected to get tighter with time as applications are modularized into increasingly finer microservices and communication stacks are offloaded to hardware. Now, since tail latency at a server is dominated by the queuing delay and not the service time, state-of-the-art schedulers are optimized based on results from queuing theory. And from a theoretical standpoint, the answers are very clear. And in a nutshell, they say that in order to keep tail latency low across a wide variety of service time distributions, a scheduler policies. First, a single request queue to avoid load imbalance across cores, and preemptive scheduling, which avoids head-of-line blocking of short-running requests due to long-running ones. Now, unfortunately, from a system standpoint, the answers are less clear. And this is because canonically implementing these theoretically optimal policies necessitates the use of mechanisms which have high overhead. And this results in limiting the maximum throughput that these systems can sustain, with this fraction of sacrificed throughput only increasing as timescales grow shorter. So the graph you see here provides an abstract visualization of this sacrificed throughput. Now, implementing tail optimal policies makes these systems go from the blue curve to the orange curve. Now, this has the benefit of keeping tail latency low for a larger load, but has the drawback of causing these systems to saturate sooner than their non-tail optimized counterparts. So the question we're asking in this work is it feasible to improve the maximum sustainable throughput of such systems without sacrificing the tail latency properties? That is, move these systems from the orange curve to the right towards the ideal green curve. And the rest of the talk, I will demonstrate that it is indeed feasible to do so, and that the key to doing so is to approximate these optimal scheduling policies. And the reason for this is that approximation enables low overhead mechanisms that significantly improve application throughput at a negligible tail latency cost. So going back to the graph I showed you, approximating these policies make sure we retain the shape of the curve and keep tail latency low for a sustained load, for a longer sustained load. But the low overhead mechanisms we can now implement ensure that the curve shifts to the right and sustains a much higher maximum throughput. So we use these insights to build Concord, which is a microsecond scale scheduling runtime for data center applications. Concord not only outperforms the state of the art at today's timescales, but is also future-proof in that its performance improvements only increase as timescales go shorter, and it also outperforms the latest hardware support for scheduling. Now, the graph on this slide gives you a glimpse of Concord's results. I'll come back to the details of the results, but what I want you to take away from this slide is that the results mirror the abstract graph I showed you on the previous slide. So to summarize, if there is one thing I want you to take away from this talk, it is that approximating optimal scheduling policies significantly improves throughput at microsecond scale at a negligible tail latency cost. So here is the outline for the rest of my talk. I'll start with Concord's design and specifically talk about how it approximates both precise preemption and a single queue before presenting a few results from our evaluation and concluding. So let's start with the design. Now, before diving into details, I'm going to introduce you to a system model that I'll be using throughout the rest of the talk. The model is the one you see on the slide. We have one dedicated dispatcher thread and multiple worker threads, all of which are pinned to individual CPU cores to ensure maximum locality. And the dispatcher thread is responsible for maintaining the single queue and for sending out requests to the worker threads. Now, I want to mention that while this model covers how a majority of low latency systems are architected, it does not cover all of them. Please refer to the paper to see how systems that do not conform to this model also benefit from Concord's ideas. So given this model, let's take a look at preemption. So the state of the art to implement preemption is to use interrupts. And how this works is the dispatcher thread basically monitors for how long each worker thread has been running. And whenever the desired quantum has elapsed, it sends over an interrupt, an interprocessor interrupt or an IPI. Now, the benefit of this approach is that preemption is precise because the worker thread immediately gives up the CPU and is ready to process a new request. The downside, however, is the overhead of receiving this interrupt, which in a state-of-the-art system like Shinjuku costs about 1,200 cycles, which is approximately a 12% overhead at a 5 microsecond quantum if we assume a 2 gigahertz clock. So clearly, implementing precise preemption has a prohibitive overhead, but does preemption need to be precise in the first place? And to answer this, we ran a queuing simulation where we didn't model the quantum as a constant value, but rather as a random variable. And here you see the results for a specific service time where 99.5% of requests take 0.5 microseconds and the other 0.5% take 500 microseconds. But that is only a representative workload. We observed similar results across all workloads. And the key takeaway from this graph is that despite small variances in the scheduling quantum, the tail latency properties do not change significantly, or approximating the scheduling quantum does not significantly change the shape of this curve. So we use this observation to implement preemption asynchronously in Concord using what we call compiler-enforced cooperation. And how this works is, once again, the dispatcher is going to monitor for how long each request has been running. And this time, whenever the desired quantum has elapsed, it's going to write to a dedicated cache line. The Concord compiler is going to automatically insert probes, which frequently poll for this cache line. And so whenever the worker thread notices that the cache line has been written to, it's going to voluntarily give up the CPU. And so in effect, what Concord is really doing is it's automatically converting these worker threads from being interrupt-driven CPU drivers to being poll mode CPU drivers, which is in line with how all low latency systems eschew the use of interrupts in favor of polling due to the associated overheads. Now, this is going to approximate preemption because there is a time gap between when the dispatcher core writes to the cache line and the worker core actually reads it. But this significantly reduces the overhead because the cost of the preemption notification, which is here a shared cache line, is really the minimum cost you need to pay for two cores to communicate. And secondly, the probes, when unsuccessful, have a very low cost because all they really consist of is a read instruction in a branch, and the read is almost always going to be an L1 hit, and the branch is almost always not going to be taken, and so very easy to predict for the branch predictor. So the graph on this slide shows you, compares the overhead of Concord's compiler-enforced cooperation against state-of-the-art interrupts. And we see that the overheads are 12x lower at 2 microseconds and 10x lower at 5 microseconds. I've also shown here a naive form of compiler-enforced cooperation, which does not use cache lines, but RDTSE probes to check whether the quantum has elapsed. Now, this has significantly higher overhead, though, because calling RDTSE frequently is too expensive at microsecond scale. So that was how Concord approximates preemption at much lower overhead. So now let's take a look at how it approximates a single queue. So going back to our model, canonically implementing a single queue leads to two main sources of overhead. The first is fairly obvious, which is that the dedicated dispatcher is really not contributing to application goodput. The second is slightly more nuanced and arises due to cache coherence stalls because a single queue mandates synchronous communication between the worker threads and the dispatcher threads. And this is because to ensure optimal load balancing, the dispatcher thread can only send over a new request when the worker thread has finished processing the previous one. These cache coherence overheads have been mostly ignored by prior work because they were masked by the overhead of interrupts. But once your preemption notification is just a cache line, these start mattering as well. So now let's take a look at how Concord approximates a single queue to mitigate both these overheads. So first, to ensure that the dispatcher can actually contribute to application goodput, Concord uses a work-conserving dispatcher. So basically, this dispatcher is going to steal requests from the global single queue, whenever it notices that all worker threads are busy. Now, to ensure that it can do so while still being able to respond in a timely fashion to both events from the network and the worker cores, we actually use the RDTSE-based instrumentation I showed you a few slides ago. And the reason we have to do so is because there is no external agent that can preempt the dispatcher, and it must preempt itself. Now, this setup ends up approximating a single queue, because once a dispatcher starts processing a request, it cannot be migrated to the worker threads because the instruction pointers are different because of different code instrumentation used by the dispatcher and the worker threads. Finally, Concord also approximates the single queue by using a slightly different scheduling policy called the Joint Bounded Shortest Queue, or JBSQ. And what this does is it mimics a single queue by combining the global single queue with bounded per worker queues. And the benefit of this is the dispatcher can now push a new request to the per worker queue, and this allows the worker to immediately start processing the new request when it's done and basically hides the cache coherence stalls I told you about. Now, a natural question at this point is what the depth of the per worker queue needs to be in order to hide cache coherence stalls. I mean, of course, having a very long per worker queue will end up in a multi-queue-like scenario. But we found that for almost all realistic workloads, a queue depth of 2 is sufficient to hide these stalls. So to summarize, I've told you how Concord approximates precise preemption using compiler-enforced cooperation and approximates a single queue using a work-conserving dispatcher and JBSQ. I'll now present a few highlights from our evaluation, and I'm going to answer 2 questions here. First, what are Concord's throughput benefits at today's timescales? And second, are Concord's mechanisms future-proof, both with respect to tomorrow's timescales and with the latest hardware support for scheduling? So to evaluate Concord, we compare it against 2 state-of-the-art scheduling runtimes, Shinjuku and Persephone, which are the state-of-the-art for runtimes that really implement blind scheduling policies, that is, do not rely on application-level assumptions. Shinjuku implements both a single queue and precise preemption, and we use a version of Persephone that implements only a single queue, and this is really a proxy for, and acts as a proxy for multiple systems like Shenango and Caladan, which only implement single queue scheduling. The metric we're going to use throughout our evaluation is the maximum throughput sustained for a given 99.9th percentile slowdown. And the slowdown here is the ratio of the total time the request spends at a server to its service time. And what it's basically going to tell you is how much the request ends up being slowed down by other requests in the system. Now, slowdown is a proxy for tail latency, and the reason we use it instead of tail latency is because it becomes independent of the absolute value of service time. And so it allows us to set one common target SLO across multiple service time distributions. And so in our eval, we're going to set the SLO at 50 times the average service time, and this is consistent with prior work. So to start off, to look at the benefits for today's timescales, we're going to compare performance across multiple service time distributions. So we start with a distribution that has high variability. And so on this slide, you see the performance benefits of Concord over Persephone, FCFS, and Shinjuku for a level DB server workload that has 50% gets and 50% scans, with the gets taking 600 nanoseconds each and scans taking approximately 500 microseconds. As you can see, Concord provides a 52% increased throughput for the same target slowdown of 50x. We also evaluate Concord for service time distribution with low variability. I want to emphasize that this is really an adversarial workload for Concord, because for these workloads, preemption doesn't really help. And so the first come, first serve, or the single queue policy is really optimal. And what we see is that Concord still continues to perform favorably with respect to an optimal policy and outperforms Shinjuku because of its lower overhead mechanisms. We then evaluate Concord at future timescales. So what we do is we take the level DB workload I showed you from 2 slides ago, and we use a scheduling quantum of 2 microseconds instead of 5 to really prioritize the short requests, which take only 600 nanoseconds. And what we see here is that the performance improvements scale and improve, and they become 83%. And this is really because Concord's low overhead mechanisms really start to shine as the timescales grow shorter. Finally, to compare Concord against the latest hardware support for scheduling, we compare Concord against user interrupts, which is this x86 feature that they've recently launched in their Sapphire Rapids processors. And we see that Concord continues to provide a 2x lower overhead than user interrupts, which, if you think about it a little more, should not really be all that surprising, because a shared cache line continues to be the fastest way for two cores to communicate. And even interrupt delivery, which requires writing to memory map registers, ultimately ends up relying on the same cache coherence mechanisms. The paper has a lot more results, including throughput improvements for many other service time distributions, a detailed analysis of how each mechanism contributes to these throughput improvements, and an analysis of how our compiler overheads change as we change the application. So we actually evaluate the Concord overhead across 25 benchmarks from standard benchmark suites, and we show that it remains to be low in approximately 1%. So to summarize, today I told you about Concord, which is a microsecond-scale scheduling runtime for data center applications. And Concord's key insight is that approximating, as opposed to canonically implementing, theoretically optimal scheduling policies gives you significant throughput benefits at microsecond scale at a negligible tail latency cost. Concord is part of a larger project at EPFL that we call performance interfaces, where we're building systems that make it easy to reason about performance. And Concord is a key aspect there because Concord's compiler-enforced cooperation allows us to really bound execution time at very low overhead. If any of that sounds interesting to you, please come find me after the talk. Concord's, the code and the paper are available at this URL. Thank you for your attention, and I'm happy to take questions.
Thank you, Rishabh, for an awesome talk. Questions? Margot.
Hi, Margot.
Hi, Margot Seltzer, UBC. Thank you for a lovely talk, and I think the work is fantastic. I'm wondering if there are certain workloads under which having the dispatcher process requests ends up making the dispatcher a straggler. And I guess I'm wondering if you've seen that, and if not, why not?
Great question. So this actually dovetails really well with JBSQ. And the reason is, so the dispatcher is only going to pick up requests when all the worker threads are busy. And JBSQ ensures that you have 2 requests at each server. So it's only going to pick up requests at high load. And although the RDTSC instrumentation does slow down the dispatcher, at high load, this ends up being a lot less time than the amount of time this request would spend bouncing around queues. And so we have quite a detailed theoretical analysis in the paper, but it was something we worried about, but it didn't actually show up in practice.
Question on the left.
Hi, great talk, really cool work. Shaurya Patel, UBC. I had a question about JBSQ. I have 2 questions actually. When you put a request to the per core queue, do you also move it around to different cores once it's put in the per core? And if you don't, then have you looked at the cache statistics? Because if you have a global FIFO queue and you put it to a different core, then the working set of small requests might be small enough that you might be gaining a lot from that. So I just was curious about this.
I'll answer both. So firstly, yes, when a request is preempted, it comes back to the global single queue. And so it can then be moved to any other queue, depending on which queue is empty at that point in time. Going back to cache behavior due to migration of requests, that is something that is a concern, but it's a very application-specific concern. And we think it's an orthogonal concern to Concord, but it's something that Concord is well suited to deal with, and I'll tell you why. So Concord separates 2 concerns. The dispatcher decides which request goes where and how long it's going to execute for. And so it allows for you to implement scheduling policies that take into account locality. So you could always try to send a request to the core it was last processed by. That is orthogonal to Concord's mechanisms, so the policy you implement is, that's why we did it.
Cool, thanks.
Stefan, next to you.
Very nice talk, Stefan Soroyo, Microsoft. I was wondering whether if you don't have access to the source code, and if you have to rely on maybe binary modification, would Concord still achieve these kind of benefits, you think? Or I don't know, can you comment on such a scenario?
Great question. So the prototype now does require access to the source code. And we don't think that's a problem when you're trying to deploy your own VMs on the cloud or private cloud workloads. We would really like to remove this limitation by using binary analysis. It's something we're going to explore in the future, but we haven't tried yet, so it's not something I can concretely complete.
Richard Black, Microsoft. What are you doing about avoiding starvation for the requests that take longer than your quanta?
So those requests come back to the single queue, and they end up being, they make their way to the single queue, and they will eventually get processed. So there is always liveness in the system. Now, because Concord has a centralized dispatcher with full visibility of all worker threads, you can implement whatever scheduling policy you want. And so if you are particularly worried about these long requests, or maybe you have a large fraction of these long requests, then you can implement a policy that suits them. That is orthogonal to the mechanisms underlying the runtime, and so that's not something we addressed here.
Thank you.
Let's thank our speaker one more time.